This video will be a quick survey of our solar system. So let's take a little tour about what we know in general about the planets. Future videos will give more detailed information, but let's go ahead and start here. A little slice of the sun off to the left. There are two groups of planets. There are the four terrestrial planets, the rocky small planets near the sun: Mercury, Venus, Earth, and Mars. There are four gas giant planets, the Jovian planets, the outer planets, that Jupiter, Saturn, Uranus, and Neptune. The dot out here when this slide was made, Pluto is a planet. We'll get to that, why it's no longer in that category. The two groups, the rocky small planets near the sun, the large gas planets far from the sun. And there's a reason that they have this distinction. If we look at the planets from time to time with the telescope, we could see their angular sizes represented here. They're not always these same angular sizes. Venus is the one that this graphic especially illustrates the change in the angular size. When the planet is close to the Earth, then we see a large image. When it's further away, it is smaller. So that happens for all the planets, but they're just illustrating here for Venus. But we do have a better view of Venus and a little bit Mars than, say, Uranus and Neptune that are further away. Even though they're large, they're hard to view, they're small. Sort of a layout here with the familiar football field, and taking a look at this diagram. It's not completely to scale. The planets aren't this close to the surface of the sun, but let's just concentrate on the spacing of the planets. That's the main emphasis of this graphic. So Mercury, Venus, Earth, and Mars, again, just packed in here to about the 5-yard line, within the 10-yard line of the football field. Jupiter at the 17-yard line, Saturn at the 30, Uranus at the its orbit takes a little range of distances, but let's say 63 yards away from where the sun is, and then Neptune 100 yards from where the sun is. So there is a great spacing on the outer planets. The inner planets are a little bit closer to each other than the outer planets. And if you wanted to lay out the sun here, smaller than a golf ball would be its size. So let's talk about masses. This shows the mass of three objects in the solar system: the sun, Jupiter, and Saturn. Everything else just doesn't even get a line as far as the mass on it. But the sun completely dominates the mass of our solar system. Jupiter, you can see a little trace of red area here, and Saturn, just a green line practically on the edge of this pie chart. It's all sun. The sun completely dominates the mass of our solar system. Jupiter is next, and if my memory serves me right, Jupiter has more mass than the other 7 planets put together. If we get rid of the sun to excuse our view, then here we are with the planets. And Jupiter, my memory's correct, Jupiter is this big slice of the pie, and then Saturn, and then we have Uranus, Neptune, and then the rocky planets are very difficult to view in here as well. They're very small mass compared to the gas planets. So Jupiter, Saturn, Uranus, and Neptune. And Neptune has a little bit more mass than Uranus. But the gas planets have much more mass than the inner rocky planets. There's a reason for that. We'll get to that. Let's go ahead and take a tour of the planets with some images. Mercury, a object not too unlike our moon. Lots of craters, no water on the surface, no atmosphere to speak of. Might have a very tenuous atmosphere, temporary atmosphere. But because there is no weather, no atmosphere, no rain, weathering, the craters that are made when rocks impact are very long-lasting, long lifetimes, and we still see them just as we see them on the moon. Venus is completely cloud covered. Everything you see here are clouds. Even the dark areas here, there are clouds in those regions. We can never see the surface of Venus from the Earth, from our telescopes in orbit around the Earth. However, we can penetrate through those clouds with radar. And several years ago, there was a spacecraft in orbit around Venus that had a radar instrument and mapped out high regions. The brighter areas here are higher elevation, and the dark areas are lower elevation. There was mapping that found craters on Venus and found volcanoes on Venus. So Venus will be a very interesting planet to talk about and compare to the Earth, as we'll compare all the planets in future lectures. And mystery planet, yes, you're correct, it's the Earth. Lots of blue ocean, clouds, United States in the image here. And we have very good imagery of our world, of course, because we have many satellites that orbit other hemisphere with Africa, and really nice place to live. Our astronauts have gone to the moon, and as they circled the moon, they took a photograph of the Earth. If you were standing on the moon, you would see the Earth go through phases of new Earth, crescent, quarter, gibbous, full Earth. You'd see the whole range of phases. They'd just be opposite to what the moon's phase is. So at the time of new moon, you would be standing in darkness on the surface of the moon. The Earth would be full. But the Earth does go through phases as viewed from our moon. Our Earth-Moon system is unusual in the solar system. Our moon is very, very large as a proportion of the Earth. It's a large moon compared to its host planet, compared to any other satellite of a planet in our solar system. We have an unusually large moon. Mars, interesting thin atmosphere planet. We have volcanoes, and we're seeing clouds above those volcanoes. They're not active right now, they're dormant volcanoes, but certainly had a big influence on the atmosphere of Mars in the past. We've sent many spacecraft to Mars, United States, Europe, Soviet Union, and there have been some very successful ones recently. The Spirit and Opportunity rovers were solar powered. You can see the solar cell here, and roamed around for several years. The Spirit rover is no longer operational, but its twin, the Opportunity rover, is still in operation, taking measurements, returning photographs, and I should look this up ahead of time, but I think it's been going for 10 years. It's been driving on the surface of the moon for 10 years with this solar power capabilities. And then a couple of years ago, this is being recorded in 2014, a couple of years ago, the Curiosity rover landed, and nuclear powered, and doing a good job of exploring the region where it landed. These rovers have found evidence of water in the past. There was liquid water on Mars in the past. None currently, but there is ice underneath the soil of Mars, and much remains to be investigated about Mars. Another view of the panorama, and this rover is headed up the slope of Mount Sharp in Gale Crater, and taking measurements along the way, and testing soil, looking for the possibility of a habitable environment in the past. It's not looking for life, this rover, but looking for just the conditions of the past in Mars. Then Jupiter, the planet with the red spot, and this red spot circulates. It's an atmospheric feature. These are all clouds that you're seeing here, and mainly hydrogen and helium in the gas planets. This spot has been observed since telescopes had good enough quality to observe details in the atmosphere of Jupiter. So over 300 years, this red spot has been present, and we know it is circulating, it's spinning in the atmosphere of Jupiter, a atmospheric feature that's lasted for over 300 years, and a mystery as to really what's going on. Then Saturn, the famous ring planets. These rings are just millions upon millions of little chunks of ice and ice-covered rock that are in orbit around Saturn. The rings are not solid. You can see Saturn through the rings. You can see stars through the rings. That'll be an interesting planet to look at as well. And then Uranus has rings also, very faint rings. Jupiter also has rings, faint rings. But Uranus has a strange angle of its axis compared to its orbit. The Earth's axis tilted 23.5 degrees, but the tilt of Uranus is a little over 90 degrees. So that gives strange seasons on Uranus. Neptune also has some atmospheric storms in it, atmospheric features that are not as long-lasting as the red spot, but very cold atmosphere, interesting as to what's going on. And then Pluto, discovered around 1930, used to be a planet, but late 1970s, a moon was discovered going around Pluto. From that, astronomers could calculate the mass of Pluto and discovered that Pluto is less mass than our moon. Pluto also has a strange orbit. It's this outermost one here. This is a comet orbit that's been put into this graphic, but the 8 planets have pretty much orbit in a plane. Pluto's orbit is more oblong, more eccentric, and also has an angle compared to the plane of the 8 planets. So it goes up above the plane and down below the plane. But Pluto will be worth talking about in the future. So lots of properties that we can identify for the planets. Some of them here, mass. How do we determine mass of a planet? Well, we determine it from its gravitational effects. For Mercury and Venus, it's from spacecraft that fly by the planet and how the orbit of the spacecraft gets deviated by the pull from gravity of the planets. Earth, we can measure the mass using Newton's law of gravity and measure the acceleration of gravity on the Earth. Let's go out on to Mars. Mars has 2 moons, and from the study of their orbits, the mass of Mars can be calculated. And from that, density can be calculated as well. So this table just shows the mass. The Earth's mass, roughly 6 times 10 to the 24th kilograms. It's pretty fine print over here, but 10 to the 24th kilograms is being used for this row. So the law of gravity and the nature of circular orbits or of orbits can be used to determine the mass of a planet. Look at Jupiter, 1899 for its mass. The Earth's mass is 6 on this scale of 10 to the 24th kilograms. And then Saturn, also significant, 568, Uranus, 86.8, Neptune, 102, Pluto, 0.0125, and here's our moon, 0.07, Pluto, 0.0125. So gravity is used to determine the masses. Diameters can be measured by measuring the angular size of the planet and knowing how far away it is. And the how far away it is a crucial feature that allows some of these items to be calculated. How far away it was determined relatively in the 1500s, and people set up the AU, the Earth-Sun distance, as kind of a ruler in our solar system. And by the study of angles to the planets and some geometry, the relative distances to the planets can be worked out, how big their orbits are in AUs. Better values came in the 1900s for the AU, some number of meters, and by doing parallax measurements, astronomers came up with a value for the astronomical unit. But in the 1960s, using radar to actually bounce radar off of Venus and detect its return, measuring that time delay gives a distance, and very good values for the astronomical unit were achieved in the 1960s. That's a little bit amazing. That's not too long ago for me. So maybe for you it sounds a long time ago, but just thinking that astronomers didn't have a really solid value for the astronomical unit until the 1960s is amazing. The parallax number giving the astronomical unit did not disagree wildly from the radar unit, so there was not a big revision of the solar system. But just still kind of interesting that that measurement of the AU was not in the too far distant past. So gravity is used to determine mass. We use the angular size and the distance to the object to determine diameter and calculate then the volume. There's a formula that we're not going to use, but if you know the radius or diameter for a sphere, then we can calculate the volume. The planets are basically spheres. Gravity pulls things down into a spherical shape. That's why our planets are not some oblong structures, not some rectangle, but go into a circular shape. Gravity pulls things into a circular shape. So with that volume, you can do mass divided by volume and come up with the densities of the planet. So that's an interesting row right here on this table, the density. Mercury 5.4, Venus 5. Oh, I'm sorry, we're in kilograms per cubic meter. So 5,400 roughly for Mercury, 5,200 for Venus, 5,500 for the Earth, 3,300 for the Moon, a little bit different, and around 4,000 for Mars. And then Jupiter, 1,300, Saturn, 687, 1,270 for Uranus, and 1,638 for Neptune. But look, there's a change in the densities. 5,000, 5,000, 5,000, 3,000, 4,000, and then Jupiter drops down to 1,300, so around 1,000 for these outer gas giant planets. The density gives us a clue on the structure of the planet. The inner planets, the terrestrial, these are kind of the density of rock and compressed rock, but nonetheless densities that are rock and iron, core type objects. We'll talk in detail about the structure of each planet. The outer planets are consistent as being gas and perhaps some solid core in the middle, but essentially gas comprises the outer planets. Saturn, this density is less dense than water. If you had a big enough bathtub and the gas had a little bit more structure to it, you could float Saturn in water. Saturn has a density smaller than water. Calculating the surface gravity, so that's fine. The escape velocity goes with that. Then the rotation period in hours, how long it takes to spin. Earth is 24 hours. Venus is interesting. It spins backwards compared to the Earth's direction of spin. Same for Uranus. It spins backwards. And the gas planets generally have a small time for their day, for the one rotation. You know, Jupiter here at about 10 hours. And Mars and the Earth about the same, around 24 hours. Mercury and Venus spin very slowly. And the Moon, of course, a 29-day spin. Length of day, so that's fine. Mean temperature. Mercury, 167 degrees Celsius. So that's above the boiling point of water. Venus, way above the boiling point of water. The Earth, 15 degrees Celsius is our mean global temperature. Surface pressure, no atmosphere for Mercury, very thick atmosphere for Mars. We've got 1 unit of atmosphere, the way this table's been calibrated. No atmosphere of the Moon. Very thin atmosphere for Mars. And number of moons, 1 for the Earth, 2 for Mars, many for the gas giant planets, over 60 for Jupiter and Saturn. And the ring system, the outer planets, yes, the inner planets, no rings. Global magnetic field, Mercury has a magnetic field, Earth does. And then the gas giant planets have a magnetic field. So some interesting properties there. There are these two categories. The rocky planets near the sun have a certain set of properties that are similar, few moons, if any, higher density, less mass. The outer planets, more mass, more moons, and just a different category. The terrestrial and the jovian planets, and we'll emphasize those as we talk about their properties as we go through this chapter, and using astronomynotes.com for the material for my class. So you ought to think about viewing these planets, and we like to photograph them and so forth. When's the best time to view one of the outer planets? Mars or Jupiter or Saturn, Uranus and Neptune? Well, to get a good picture, we'd like them to be close. So you ought to pull out a little sheet of paper, put the sun, of course, at the center of the solar system, draw a circle around it for the Earth's orbit, and then draw a bigger circle for one of the outer planets. So take the sun and the Earth as fixed on your piece of paper, put a definite E on the orbit for the Earth. Where should this outer planet be in order that we get the best view of the outer planet? And you should have this outer planet on a straight line with sun, Earth, outer planet on that straight line. When the planet is opposite in the sky to the sun, that's called the time of opposition. Opposition. The planet is 180 degrees away from the sun, and this is the best time to view a planet through a telescope or take photographs of it because it will be at its closest. Now, refining this a little bit further, our planet orbits are elliptical, not circular. So would you want the Earth to be at perihelion and the outer planet at perihelion? Is that the best? Or should the Earth be at perihelion and the outer planet at aphelion? Or should the Earth be at aphelion and the outer planet at perihelion? Or should the Earth be at aphelion and the outer planet at aphelion? What will produce the closest approach of the two planets? And they never get extremely close, but what would make the best picture? Well, it's going to be the Earth at aphelion. We want the Earth far from the sun, and we want the planet as close to the sun as possible, so that's perihelion. So Earth at aphelion, outer planet at perihelion. So that's connects with some of the things that we've talked about before. So we've explored our solar system a little bit with spacecraft, not extensively. Most of our knowledge of the inner planets does come from spacecraft flying by close and taking photographs, including Mars, and landing on Venus and Mars has occurred, and of course our moon, the Apollo program, those landings. And having instruments on the surface is greatly desired, but difficult to do for the planets. When we get to the outer solar system, we have to rely on more photography and the study of absorption lines and the spectra to give us some more clues as to what materials are in the clouds of those planets. So a little bit of remote sensing is a means to discover what's happening in those planets. Another table here, the distance from the sun and perihelion distance, aphelion distance, orbital period, and so forth. The orbital eccentricity, I'm going to stop on this just a little bit. Mercury's orbit is not circular. It's definitely elongated, so 0.2 for its eccentricity. Venus, very circular, and the Earth, 0.017. Mars, a little bit more eccentric orbit, 0.09. And then the outer planets, more circular than that. Pluto, 0.244, the greatest eccentricity in this table, the most elongated orbit. If you remember, the eccentricity number goes from 0 up to just short of 1. And the axial tilt on the spin axis, again, Venus spins the wrong way, so it's 108, almost 180 degrees for the tilt of its axis, 23.5 for the Earth. Very similar for Mars, 25. And then Jupiter doesn't have much tilt, and got about like the Earth here for Saturn. Again, Uranus spins backwards compared to the other planet, most of the other planets, and then Neptune, Pluto also spinning backwards on this scale. So that's an introduction to the planets. You should definitely keep reading, and we'll do some more in future lectures.